The next problem we're going to take a look at is binary search. And specifically, we're going to show how we can do a recursive version of binary search. So in case you don't remember binary search, what we can do is look for a specific array element using the fewest number of comparisons. So the idea was that we would divide the array in half. So then we would figure out which half we want to take a look at, the lower half or the upper half. And then we would divide that half again, picking a lower or upper half, and we would keep repeating this until we find the element. So what we find here is we can actually transform this loop into a recursive method, and this process is very, very easy to do. So if you remember from the binary search code, and if you don't, I suggest you to look it up, we had these low and high variables that we set, and then we would go back to our while loop. So what we would do now is our low and high would be parameters to the method instead of just declared within our method. And what that means is instead of having to change the low or high variables, whenever we call binary search, we would just update the values of those parameters. So we have a low and high parameter, and we would just change them there. So when we do that call of the binary search, we already have our new range. And what this means is we no longer need to use a while loop. The repetition part of it will be taken care of with each call to the binary search method. Here's the code for the recursive version of binary search. And what we find here is we actually have two different methods. So this method up here is going to be the original call. So whenever we call binary search, this is what we're going to call. And notice that inside of here, we're going to call the second version of binary search, where we pass the lower bound and upper bound of where we want to search. So initially we want to search the entire array, so our lower bound is going to be 0, and our upper bound is going to be size minus 1. So now we're going to deal with the second version of binary search, and this is our recursive method. Now you should notice that the first several lines, so this whole section right here, right there, this is no different from our original binary search. So we're finding the midpoint, so that's our mid, and if it equals the key that we're trying to search, well, we return mid, and we find that if low is greater than high, then that means our lower bound and upper bound have crossed over each other, which means the element does not exist, so we return -1 to say that value that we're looking for, the key, does not exist in our array. So all that's the same from before. The difference is what comes afterwards. So this section right here. So notice that what we do here is we're still checking a mid with our key. And so if a mid is less than key, what we did before is we would set low to mid plus 1. Now what we do instead is we call our binary search method, and we just pass the new value of low. So we pass mid plus 1 to be the new value of low. And if a mid is greater than key, normally we would just set high to be mid minus 1, but instead we call binary search, and we just pass the updated value of high as a parameter. So I want to make just a couple more notes about the code that we just saw. So notice that we actually overloaded binary search because our first call would pass the initial low and high values to our second method. Now I could rename the other one to be like recursive binary search or something like that, but it's not necessary. We can take advantage of overloading in Java or in C++. Now in other languages that might not be possible, and you may need to use a different method name, but if you're implementing this in Java, then you can overload the method. And what we see is that each recursive call would cut the search area in half. So it does let us get closer to the base case. But what is the base case in here? Well, we actually have two base cases. One base case is that we find the element that we're looking for, so we just return our mid. Or then the other base case is we don't find it at all, and we just return -1, and we're done. Now we find that this recursive approach is still O of log n time. That part hasn't changed. So the code itself is a little bit more elegant, but from an execution standpoint, it is slightly slower. And that's because there is this extra overhead with making all of these additional method calls. Now we just mentioned that with the binary search approach, because we're calling additional methods, it's actually slower than the iterative approach where we use while loops. So the question we should be asking is recursion efficient? And that's because, as I mentioned, calling a method does involve some overhead. And this is because control has to be transferred from the location of the call to the beginning of the next method. We have to deal with the arguments of the method. So then we also have to deal with the return address of the method. They all have to be pushed onto a stack. That way we know where to return whenever we're done. So there's this extra overhead. So it looks like it really isn't efficient. I mean, if we go back to our example with the binary search, our method had several calls. We had to call the method several times. So the while loop may actually be faster from an implementation perspective. And then each call also requires more memory. If we're not careful, we could get a case where we run out of memory because we just keep calling the methods over and over again, and we would get a Stack Overflow error. So it just doesn't seem like recursion is useful. I mean, why would we use recursion if it's slower than the iterative approach? Well, the reason is because it simplifies a problem conceptually. It's not used because it's more efficient. So the reason why we actually use it is because it helps us solve some problems more elegantly than the iterative approach, but it's usually a lot slower compared to the iterative approach.